Welcome back to our third and final segment. We're still exploring resistors in series. Now we want to take a look at how adding more resistors in series actually affects the magnitude of current in a series circuit. Okay, so what we've done now, we are able to understand that in the context of circuits, right? We've got a series connection, which is our focus, and we understand that in a series circuit, the more resistors you add in series, the greater the effective resistance of that particular circuit. Now we want to take a look at how that exactly affects the magnitude of current, right? Okay, so in a series circuit, what is it that we notice about the current in the circuit, okay? And the potential difference across it when we add more resistors in series, okay? Because that's the context. So what we've changed is actually the number of resistors in series. So we have got two resistors. We started with one of magnitude 10 ohms, which is R1, right? So, and we managed to measure the resistance of that particular resistor, which is actually equal to the total resistance in the circuit, by measuring the voltage across the R1, and then knowing how much current, then we can use the mathematical equation. Resistance of R1 is equals to voltage across R1 divided by the current that passes through R1. Now we want to add a second resistor. However, the second resistor is actually half the resistance of R1. So R2 is actually half of R1, and R1 is double R2. Make sure that you understand that mathematical relationship. So we're saying that our first resistor is a 10 ohm resistor, okay? And then the one that we're gonna add in series is actually 5 ohms, okay? Now we are saying that R1 is equals to twice R2, okay? So make sure that you understand this, but effectively, adding the two resistors, we got the total resistance of R1 plus R2, which is actually equals to 10 plus 5, which gives us the total of 15 ohms, right? So that's our R total. Now we want to understand that if we add another resistor, how is that going to have an impact on the size of current through the battery, through each one of them? But remember, in a series circuit, there's only one path for current to move in the circuit, right? Okay, so this is what we realized, is that the total resistance, if we used, let's say for argument's sake, a resistor of 6 and 3 ohms, it will give us a total of 9. Okay, the voltage was actually 9 volts because the other resistor one across it was 6 ohms. Okay, 6 volts rather, because that's the voltage, right? So, and then the total that I'm trying to refer to is actually the 15 ohms that we managed to get from the sum of these two. And then we want to verify what happens to the current in a series circuit, right? Okay, let's go to the simulation very quickly. So we've got two resistors here. The first one is 10 ohms, that's our R1. The second one is our R2, which is half R1, which is 5 ohms. The voltage across the source, whether the switch is open or closed, we realize that it's 9, okay? Now, there is no current in the circuit. Why? Because the circuit is broken, okay? But if we decide to close the switch, there is current in the circuit, okay? Now, if we start by maybe verifying the values of voltage across each one of those components. So our terminal potential difference is the voltage across the source, right? That's the voltage across the source when there is current in the circuit. That gives us 9 volts, right? So this is our V total, or terminal potential difference, while V across resistor 1 is equals to 6 volts, okay? We are verifying that. And then voltage across R2, is equals to 3 volts. So the sum of 3 and 6 volts gave us the total of 9 volts, okay? But how much current passes through R1? You realize that before R1, there is 0.6 amperes of current, okay? After R2, there is 0.6. Even if we put another ammeter would also understand that the same amount of current, even through the source, the same amount of current will pass through it. Okay, so this drives us to the the conclusion that in a series circuit, solely because there is only one path for charge to flow, then the same amount of charge passes through every point per unit time, which is equals to 1 second. Right. Okay, if we go back to our, we can verify that we had 0.6 amperes through the battery. So this is actually, the total one is through the battery. Okay, so this is the current through the battery. Okay, we need to be very careful about that, because this is through the battery. Now this is through R1. Okay, this is through R2. Right. So what do we notice exactly? Now let's take a look at how we are going to examine the results that we just collected. So the question was, in a series circuit, what do you notice about the current in the circuit? Now we are saying that the total current, I total, take note of the notation, is the current through the battery. Okay, this is the total current in the circuit, in other words. Okay, the current through the source, which is the battery. Okay, and then when we talk in terms of notation about I1, sometimes it will say the reading on A1. A1 becomes the ammeter that registers the current passing through R1. So this is actually the current through R1 for argument's sake. And then when we talk about I2, it's actually the current that passes through resistor 2, and so on. Okay, now we realize that the magnitude of current, if we can quickly go back to that, the magnitude of current that passes through each one of them is actually the same amount. Okay, so through the battery would have 0.6 amperes, through R1 and R2 it's also 0.6 amperes. What is the thinking behind that? There is only one path that current uses actually in the circuit. Right. So if we agree that, okay, that is the notation. So in conclusion, if you're saying I total is equals to current through resistor 1 is equals to current through resistor 2. So for n resistors connected in series, the total current is equal to the current that goes through each of those resistors. Hence we're saying that in a series circuit, right? Okay, this is the main conclusion. Okay, in a series circuit, current remains constant. So we use this data that we collected to actually arrive at this conclusion. Okay, current remains constant. So if a quantity remains constant, it means it does not change. Right? Okay. Now, the other one, now we want to predict what will happen to the current in the circuit when you add even more resistors. Okay, so we started with a single resistor. So if we added more resistors, what effect did that have on the total current in the circuit? Okay, so if we just to go back a little bit to make that comparison. Okay, suppose we take out resistor R2, okay, if we take out resistor R2, right, and then we complete that circuit, okay, you realize that with R1, which is 10 ohms only, the total current in the circuit is 0.9 amperes. Okay, suppose let's break that circuit and then add the other resistor so that we can actually get a sense of what happens in as far as the total current in the circuit. Take note, with only R1 of resistance 10 ohms, the total current was 0.9. What if we add R2, which is 5 ohms, which is half R1? Okay, we want to just make that conclusion, that observation. So to change that to 5 ohms. Okay, if we change it to 5 ohms, it will give us okay. That's the circuit. So R1 is 10 ohms, R2 is 5 ohms. Let's close the switch. Okay, now the current has dropped to 0.6 amperes. Okay, why? Because the total resistance in the circuit has increased. So if we increase the total resistance in the circuit, effectively we are increasing the opposition of flow of charge, which means there is greater resistance. Hence, there is lower current flow in the circuit. Okay, so that's a very important observation to take note of. Okay, so when more resistors are connected in series, what are we saying? R total in the circuit, which is the total resistance, will increase. Okay, while the total current will decrease. Okay, so current will decrease while the resistance increases. So where does this come from? Okay, remember, we did not change the terminal potential difference. Is still 9 volts. Okay, so that 9 volts is actually split between R1 of 10 ohms and R2, which is half the resistance of 5 ohms. Okay, so increasing the resistance actually, in not so many ways, what are we saying? It actually increases the opposition to the flow of charge, and the flow of charge is actually the current. So at a higher resistance, there is a correspondingly lower current, right? That's the main issue again that we need to take note of. Okay, so in a series circuit, what do you notice about potential difference across the resistors? So if we quickly go to our simulation, let's measure the potential difference across the resistors. Okay, so our terminal potential difference, to verify it once again, it's 9 volts. Okay, voltage across R1, it's 6 volts. Okay, voltage across R2, it's 3 volts. Okay, the 9 is split between the R1 and R2, and if you do the total of 3 plus 6, it gives you the terminal potential difference. That's the main thing there. Okay, right, so we realized that the 6 plus 3, okay, gave us the total of 9. So this is V total. Okay, so this is V across R1. Okay, this is V across R2, right? So if you add the 3 plus 6, and 6 will actually get that 9. Okay, so we've done that. Okay, so in a series circuit, what is it that you notice about the potential difference of resistors? In conclusion, we can say that the voltage or the potential difference across the battery is divided in proportion to the resistance of the resistors. You'd realize that V across the 10 ohm, okay, is equals to we got the 6 volts, and then V across the 5 ohm resistor is equals to 3 volts. Okay, so if you say V across R1 plus V across R2, you will actually get your V total, which is your terminal potential difference, right? Okay, so the resistance is the opposition to flow. This is what we know, and an ohm is a volt per ampere. This comes from R is equals to V over I, right? Okay, and then in closing, we understand now what happens when you increase the total resistance of a circuit by adding more resistors in series. Okay, because that's the scenario that we had. Okay, if you increase the resistance, the total current actually decreases, while the total resistance in the circuit increases. So in as far as resistors that are connected in series, two very important points that we take home is that increasing the number of resistors in series increases the total resistance. At the same time, it lowers the current. Hence, we would say a series circuit is actually a potential divider, while current remains constant. That's all we had for today. For now, let's take time to reflect on some of the discussions that we have. Otherwise, that's the gist of a series circuit. For myself, for now, it's cheers and bye-bye.